Hello and welcome to another video. In this video, we're going to be working on find the largest area of a square inside two rectangles from the weekly contest this week. And the problem, you have n rectangles in a 2D plane, and you're given two zero-indexed arrays, bottom left and top right, and they represent the bottom left and top right of a rectangle, respectively. You can select a region formed by the intersection of two of the given rectangles. You need to find the area of the largest square that can fit inside this region, if you select it optimally. Return the largest possible area of the square, or 0 does not exist anything. So let's take a look at example 1. So example 1, you can build a couple squares, but they're only length 1. So you could see like you could build a square here. This would be area 1. You could also build a square like this. Area 1, like this, area 1. So all of these are area 1. And let's take a look at example 2. So example 2, this green and blue overlap. You could build once again a couple squares of area 1 like this, or this. Or this red and the green, you could build one here, also area 1, or a red and the blue, you could build one like this, or like this. But essentially the main thing to see is, let's look at an overlapping region. Like, let's say this green and blue have an overlapping region like this, and this region is a 1x2 region. So because we have to build a square, we have to pick basically the shortest overlapping section, and then we can square that. So because it's 1x2, we can only make a 1x1. If it was like 2x3, we can make a 2x2 and so on. So that's the main thing to get from this problem. And in example 3, nothing overlaps, so we want to return 0. And if you look at the constraints, so there's 10 cubed squares, so we actually have enough here to just compare every square to every other square, and that's basically what we can do. There might be some more efficient thing, but the constraints allow us to just compare every rectangle, to every other rectangle, and we can do this in O of 1. So let's take a look at, let's make a little graph here with some squares, and let's show like how we would show an area. Maybe we can have one with numbered, not that one. Is there a numbered X and Y? I don't see it, but this is fine too. So we'll just use this and we'll just show some squares. And we'll just like make up some points. So let's say we have a square here. And we have a square, another square. Or not square, rectangle. Let's say we have another rectangle like this. So it doesn't really matter like where these rectangles are located. All we really care about is like the overlapping X region and the overlapping Y region. And if we know how big that is, then we know how big the square we can make. So in this case, the overlapping X region is 1 and the overlapping Y region is 2. We have to use the minimum of these because we have to build a square. So then the most square we can build is this. So let's figure out how we can calculate this. We'll just make up some numbers for this. So let's say this X is located at 0, just to make it easy. So let's say this is 0, 0. This point is 0, 0. Now let's say this point is, so let's see, 1, 2, 3, 4, and 1, 2, 3. So it's going to be 3, 4. Now this point over here is going to be located at 2, 2. If this is 0, 0. And finally, this point over here is going to be located at, let's see, so if this is 3, 4, this is 1, 2, 3, so 6, and a height of 6. So basically what you can do is for each square, you get two things. You can get intervals for their X and Y, like distance they cover. So for this square here, for this blue square, we can get an interval for like what's the X range it covers, and then we can do that for the other square. So let's do that. So for X, it covers a range of 0 to 3, right? Because we have like the small X value and the big X value. So for this blue square, it covers a range of 0 to 3. And for this green square, it covers a range of 3 to 6. This is the X range. And they can be in whatever order like you want. So basically you get this X range and you can sort it by start interval to make it increasing like this. So this is like the X intervals that we covered now. This is the left square, or the left rectangle, and this is the right rectangle. Oh, I think I did that incorrectly actually, because they should be overlapping. So this should be 0 to 3. Oh, it should be 2 to 6. That's a mistake. Okay, so this is going to be 2 to 6. That's what we cover, and that should be correct now. Yeah, okay. So you get an X range. Same thing with the Y range, and we can sort it as well. So our Y range for this green square will be 0 to 4. And for the other square looks like it's 2 to 6. Yeah, for the rectangle, 2 to 6. Okay. Yeah, because it's a 4 by 4. So you just take both of these and you can sort them. So if this was like 2603, you just sort them in increasing order. You get both of these ranges, and then you can figure out, like, do they overlap? So for these two, they do overlap, right? This is just like a merge intervals. Do they overlap? Meaning, if they don't overlap, then this value is going to be greater than or equal to this value. So you can just do a little comparison. Here they do overlap. And you basically need to figure out, okay, if they overlap, like how much overlapping space there is. And the way to figure overlapping space is really easy. It's going to be the minimum of the two end points, so two end values, minus the start value, start of second one. Because if you look, the x overlap is right over here, right? So right over here. So it's going to start where the second square starts all the time, right? Because we did sort the x's. So this x will start later. Honestly, you don't even have to sort them, but I think sorting it makes it easier. So essentially what you will get here is you'll get the minimum here. So you'll get 3 minus 2. You'll get an overlap of 1. And we can try this with like a couple more squares or so, but this will basically always work. So you just sort your x intervals for each of your rectangles in increasing order. And this is how much total area we have that overlaps. And yeah, because there's like a few cases, if you think about it, like one case is this blue square. I wonder if we can make it bigger. I think we can. Yeah, so if this blue square covered the green square, like this, let's say, then the area that overlaps in the x-axis is going to be this whole thing here, right? And that's why, actually, sorry, it's going to be, it can only be the area of like where the first one ends. That's why it's the smaller of the two end values, right? This value and this value minus the start value of the second square. So yeah, so this is going to be 1, and then let's do the same thing for the y, and it's going to be the same exact formula. So because we sorted our y in increasing order, it's going to be the same exact formula. So the smaller of these two values minus this value here. It's always going to be smaller of the two end values minus the start value of the second one. You have 2. And this sorting thing, basically now you don't have a bunch of cases like where, you know, what if my square's here, or what if my square's here, or here, or here, or here, or here. It doesn't really matter. It always works with this formula. That I was kind of just like guessing, checking a few times, and this is like, it seemed pretty reasonable for this to work. And so now we have our x area is 1 and our y area is 2. So easy problem, right? Like if you have a rectangle of 1 by 2, what's the biggest square you can form in that rectangle? It's just going to be the minimum of the two sides squared. So that's why it's going to be 1 squared, which is just 1. So we can try a couple more rectangles just to like show this. So I guess it's fine to get rid of this. Let's see. So we'll try like one more just to demonstrate this one more time. So let's draw this thing again. Just take two random squares. It doesn't really matter where they are. So let's just take one square here, like this. Let's take another square this time. Instead of going like up, maybe we'll take a square like this. There we go, or a rectangle. Let's say this is 0 on the y-axis, right? So let's say this is 0 and this is 0 on the x-axis, just to make it easier. So let's make these points. So this point is going to be 0 on the x-axis, and it's going to be 2. Then this point over here is going to be 1, 2, 3, 4, 5, 6 on the x-axis. And on the y, it will be 1, 2, 3, 4, 5 plus 2, so 7. This point will be 0 on the y-axis and 1, 2, 3 on the x, so 3, 0. And this point will be 5, or not 5, it'll be 4, 5, I think. I feel like that's incorrect. Oh, it's not 4, 5, it's 8, 5. Yeah. Yeah, so let's just double check. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And this is 1, 2, 3. Yeah. And this goes up to like this is basically our 0, 0 point right over here. And yeah, and then this should be 8, 5. So let's just double check. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's correct. Okay. So let's just do our squares. Like I said, the order doesn't matter. Let's say this, we can even use this right square as square 1 in this case, and you'll see like all the math still works out. So as you can see in the picture, we should be able to build, like this is this common area. So this is a 3 by 3. So that's what we should get. We should get a 3 by 3, which is 9. So let's see if this works out. Let's say this one on the right is square 1, this one's square 2. So for square 1, the distance covered is the 8 minus 3 for the x, right? So it covers 3 to 8. Then for square 2, the distance covered for the x is 0 to 6. So we'll say 0 to 6. Now, remember, we are going to sort these x intervals to make it easier for ourselves. So now we will sort. So this now will go over here. Let's actually move it over here. So here is our intervals for our x. This is the x. Now for the y, I'm just going to draw the intervals in order now because we are going to be able to sort. So for one of these, it's 0 to 5, and for the other one, it's 2 to 7. So 0 to 5 is going to go first. So 0 to 5, 2 to 7. And like I said, it doesn't really matter where these squares are. This will always work out. So let's figure out like our distance. And first of all, is there an overlap? Yes, there is, right? You can see that from the intervals, there's an overlap. Now remember, our formula is the minimum of the two ends. So 6 minus the starting point of the second one. So 6 minus 3 is 3. So that's our x distance of a side. Now here's our y. Do they overlap? Yes. Same thing. Smallest one of the two ends. So 5 minus the second value, 2. Get 3. So we get the side, the overlapping area in y is 3. The overlapping area is 3 in x. And it works again. So this is basically just like, you know, when you get these problems, just like try out a few numbers and print your result to make sure your formula is right. But it's literally just like, given 4 sides of two rectangles, can you figure out the overlapping area? Just some basic math kind of stuff. So now that we get the 2 sides are 3, we take the minimum side, which is 3, and we square it, and we get 9. And so this is the square that's made. And you literally just loop through for every single index, compare it with every other index, just an n squared basic brute force solution. So let's take a look at the code. Here it is. So I made a helper function that gets the overlapping area. So this is the bottom of square 1, the bottom left of square 1, the top right of square 1, bottom left of square 2, top right of square 2. And then we have our x intervals and y intervals over here. So I sort it. So the x interval for the first square is bottom 1, 0 to top 1, 0, right? Because top is always going to be to the right of bottom. That's in the constraints. Same thing for the second square. Get the same thing for the y intervals for them. Then I just check if there is no overlap, return. And if there is no overlap, meaning if the start of the second interval is greater than the end of the first interval or equal to it. Same thing for this. If there's no overlap, just return. Otherwise, literally the formula that I said. So you take the minimum of the second value in the x intervals and the second value in the y intervals, the second value in the second interval for both of them, minus the start of the second interval. Same thing for the y. And then you just take those two sides, you take the minimum value, because if you have a x by y rectangle, the biggest square you can make is the minimum of those two sides, and you square. And then you basically just brute force, compare every single rectangle with every single rectangle, get the max result, and return it. And this does run kind of slow. There might be like a better solution, but at least this one, because the constraints are kind of big. So this is, let's see here. This is 10 cubed. So 10 cubed squared is like 10 to the 6th. So it's like right barely passing. So most of the solutions I've seen around this, like 8,000, 4,000, 5,000, basically just depends on like how complicated your overlap function is. You can probably make it like a little bit better or worse. But yeah, that's basically like all there is. Like I said, you can probably optimize this a little bit because it gets called so many times. Slide optimizations here will make it run faster, but the time complexity will still be the same. So we can say the time will be O of n squared because we're just comparing every square to every other square. And then the space will be O of 1 because we don't really need to like store anything. We just make some basic things that only have 2 values, right? Like this x intervals is 2 values, this y intervals is 2 values. Even though we're only sorting 2 values, so that costs us nothing. And the min and all that stuff. So yeah, literally just a brute force problem. I'll have to recognize you can do it with brute force. Maybe there's a better solution, but I'm just gonna do this for now. And it looks like the third and fourth problem are basically the same thing with harder constraints. The easy problem is super easy, so not going to go into that one. So I'll just make one video for the third and fourth problem once I do that. I haven't done that yet, but once I do, I will post that as well. So thanks for watching, and I'll see you next one.